Hi everyone, and welcome back to my flight mechanics class. So today we're going to be covering the aircraft response in the case of the sum of the moments, and that would be the time rate of change of angular momentum. So the goal of this lecture is to establish the equations of rotational motion, and the book makes it easy because it gives us a standardized 6-step procedure to reach the time rate of change of angular momentum. So let's first remind ourselves what angular momentum really is. H is equal to the position vector r cross the mass times the velocity v. And essentially what we need to do here is to find the individual components that make up the angular momentum h, and that will be the position vector r and the velocity vector v. So instead of considering the whole aircraft right away, what we're going to do here is to start with an elemental mass dm that is part of the aircraft, but is located at a distance rdm from the center of gravity, and it is rotating about the center of gravity of the aircraft with rates equal to pq and r. So rdm is defined to be equal to x of I plus y of j plus z of k, and again, it is rotating about the CG of the aircraft with rates pq and r. So the next step is to actually find the velocity of that elemental mass dm as a consequence of its rotation about the CG of the aircraft. And that is going to be equal to drdm over dt plus omega cross rdm. And that would be the transport theorem. Now, because the aircraft is actually assumed to be a rigid body, rdm is going to remain constant, and the derivative of a constant is equal to 0. So vdm is equal to omega cross rdm. So we're going to solve a cross product with a matrix, and what you essentially get are the components of the velocity vdm. And that will be qz minus ry for the I component, rx minus pz for the j component, and py minus qx for the k component. So the next step is to figure out the linear momentum of the elemental mass dm. And this is actually pretty simple because all you have to do is to multiply the velocity that we have just found by dm. And I do emphasize that it should be dm and not m because we haven't integrated over the entire aircraft. We're still talking about that elemental mass dm. So the next step, now that we have rdm and vdm, is to compute the angular momentum of that elemental mass dm. And this is based on what we have figured out at the beginning of this lecture, and that is rdm cross dm times vdm. And again, I do emphasize that we're talking about d of hdm and not hdm because we're still talking about that elemental mass dm. So we're going to solve for that cross product again via a matrix, which is basically the standard procedure. And what you're essentially going to get is this. So the first line is your matrix operation. The second line is what you get when you develop the first line, and the third line is when you actually isolate your p, q, and r parameters for all three components I, j, and k. And this is something that you really need to do, as you're going to see in the following equations. So these would be your components, and that is d of h of x, d of h of y, and d of h of z. And we see that the p, q, and r parameters are nicely separated from the rest of the equation. And this is very important because we can actually replace the parameters that are not p, q, and r by integrations. And the reason why we do that is because we now want to integrate over the entire aircraft to get the angular momentum and the angular momentum components for the entire aircraft and not just the elemental mass dm. So p, q, and r can actually be separated because we are not a function of the mass of the aircraft. The next step is to replace the integration parameters by their corresponding moments of inertia and products of inertia. A moment of inertia is essentially the equivalent of mass but in rotation. It is a measure of resistance to angular acceleration, and this is about a given axis. The products of inertia are essentially a measure of mass symmetry. So now you have your angular momentum components for the entire aircraft as a function of the moments of inertia and products of inertia. But before we move on to the next step, there's actually some simplifications that can be done. As you can see, we have two images. On the left, we have an aircraft from a front view, and on the right, you have an aircraft from a top view. On the left, you can see that the left part of the aircraft is symmetrical to the right part of the aircraft. And that means that any products of inertia containing yz can actually be equated to 0. And this is going to be a simplification. And then on the right side, you can see that the left side of the aircraft and the right side of the aircraft from the top view are also symmetrical. And that means that any products of inertia that contain xy can also be equated to 0. And this is essentially what you would get. So these are your simplified angular momentum components. So the last step is now to find the time rate of change of the angular momentum. And essentially what you want to find is the time rate of change of the inertial angular momentum. And that is equal to dt expressed in the body axis system plus omega b cross h of b. So we have two components here essentially. We have the omega b cross h of b, and we have the dHdt expressed in the body axis system. So we're going to start with omega b cross h of b, and this is going to be solved via a matrix, and the result is what you get at the bottom. For dHdt, what you're essentially going to do is you're going to be applying the product rule. So first you take the derivative of the p, q, and r components, and then you're going to take the derivative of your I parameters. Now, because we assume the mass distribution to be constant for the aircraft in question, your I components can actually be equated to 0. So what you would get at the end after that simplification would be your equations of rotational motion. And L, m, and n are equal to the sum of the moments about the x-axis, y-axis, and z-axis respectively. So that's it for today. Thank you very much. See you next time.